Good evening, sir.
Good evening, Swati.
Sir, I'll make you a presenter so that you can share your screen.
Yes.
Yes, sir, your screen is visible.
So, shall we start or wait for some time?
Sir, I think we can wait for 2 to 3 minutes, at least till 4, 5, then we can start.
Okay. Okay, so Swati, should we start now?
Yes, sir, we can start. On behalf of VICT Academy and
Session
MNIT Jaipur, sir, we welcome you back for the session. And I'm sure that this session will be very much useful for all the attendees. You can take over the session, sir.
Okay. Okay, so welcome everyone. I hope some of you might have tried to simulate some antennas. So in today's class, we are going for the substrate integrated waveguide. So yesterday we have covered up to MIMO antennas. Now we will move our focus to this substrate integrated waveguides and how we can simulate those. So first we start with a new project. Then we select this new design. So we insert this design. Now a new design has been selected. Now in order to simulate the waveguide, we need to have wave ports, and for that we will be using this simulation solution type as model solution, and click here. So now this has changed. Now before we start with substrate integrated waveguides, substrate integrated waveguide is basically let me share you bring some document. Okay. So what is a substrate integrated waveguide? It is a planar alternative for waveguides. So waveguides, if you go for waveguide, we can see that waveguides are 3D structures. Waveguides are hollow pipes. They can be rectangular or they can be circular. All these metallic pipes are can be treated as waveguides. So the wave propagate from one end to another end, and it gets total internal reflection inside this waves. Okay. So uh, the, what are the advantage of having waveguides? So first of all, if you consider these close boundaries, what they will contribute to. Whenever we have a close boundary, that means our signal is trapped. So that signal is not going to be coupled with any other object or any other antenna. So if we have SI waveguide based antennas, then those antennas will have better isolation than our alternative than the open structure of open stub structures like microstrip. And another advantage that we get with waveguide is their better power. They are better at power handling. So we can we try to simulate these waveguides, and as these waveguides have huge sizes, so we cannot directly integrate them. Okay, so we cannot directly integrate them inside our planar structure for such a PCB. In a PCB, we cannot directly integrate the waveguides. So what imagine if we are able to integrate the waveguide in PCB. So there is an alternative way. So what happens inside a PCB, we have a ground layer. then we have a substrate, and then we have another copper layer. So this is a typical diagram of PCB in which we have put some holes. So why these holes are there? So these holes will act as a short circuit. We will be putting some conductive material inside these holes so that it connect it create a short circuit part between the top conductor and bottom conductor. So in this way, we will be having some short circuit paths here, and there is a small gap. What happens if we make a continuous boundary? Then that continuous boundary will cut out some part of the PCB. That is why that is not a feasible solution. So we select this kind of structure in which we make some wires, and those wires we can fill with metal. Okay. So first, let us see how we can create this. Go to draw, and from here we are going to start with from y equal to 0, and select this one. Now give it a size. We are starting from minus w by 2, 0, 0, and it will extend. Let us take w as 15 mm. Let us design this waveguide for 10 gigahertz. So at 10 gigahertz, the size of the waveguide should be lambda by 2, and lambda we can calculate from 300 by frequency in gigahertz in mm. So the lambda will come out to it at 10 mm. So let us take this 15 mm in size and click OK. Now the width of this waveguide is 15 mm, and I am selecting this length as 100 mm and click apply. So now if we fit this, this is a single strip, and I am changing some of its properties. Someone has any query? Okay. So now our strip looks like this. Now we create another material. This okay, this is a sheet. Check its height to P.007 mm. So now it is a solid. Second object, we give it material as, go to edit, give it material copper, and click OK. Now click OK, and then in second object we will say substrate, and the material for the substrate we will selecting green color, and the height it is starting from a thickness T, and the length is L. We are giving it 100 mm. The size is H. We will take 1.524 mm. Those are the standard parameters for copper thickness and substrate thickness. And go to here, change the material, click OK. So this one is your bottom layer. Let's say it is the ground. Now create a copy of this one also. Create a copy of the ground and say it is top. Now start it from H plus T and give it length L. This one is also L. Okay. So now if we rotate, we can see that there are 3 layers: copper, this is conduct copper, this one is copper, and this one is substrate. So it is basically a parallel waveguide because these n terminals are not closed here. Now, in order to simulate a waveguide, we need to have these walls also. So I will be giving this as starting from W by 2 in y-axis 0 and starting from T. The thickness of this sheet I am taking as 0.007 equal to the T, and length is L. Z size is, it is according, sorry, we started with 0 and it will extend up to H plus 2 times of T. And it is made up of vacuum, so we set it to copper. So now you can see we have added one wall here, side. We are making it a side 1. Now what we can do, we can select this and create a mirror copy along XY plane. So you see right now the mirror copy is like this. If we go to this top view, you will see this is the mirror copy. So now we set its properties. We are selecting base position as 0. Our mirror is placed at 0, 0, 0, and it is extending in y and z plane. So the normal of this yz plane is x-axis. So in x we are giving 0, sorry 1, and for others we are giving 0. Now click OK. Now if you see, this is the waveport. This is our side and this is our side 1. So now what we have done, we have made a continuous spread. We have made a continuous wall here. Now this is an exact replica of a dielectric field waveguide, but it has a very small height. Okay. Now go to the front view and we select the face of this substrate. Now we select this face, right click here and go to edits, go to surface and create an object from this surface. Okay. Then go to the back side also, again select the face, right click and go to edits, surface, create an object. So now we have two objects from this created from these surfaces. If you go to isometric view, click fit all, then you will be able to see the one sheet is here, another sheet is here. So now right click on this sheet and give this sheet, go to front, make this fit the window, right click here, go to excitation, go to port and assign it a wave port. So now in wave port we have to assign a new line, and this is the integration line. Now click OK, finish. Same thing we will be doing in the back side. So in back side also we select this sheet, right click on this, go to excitation port and wave port, select this one and okay, so it is saying invalid parameter, so I might have taken something. Redesign this. Okay, now it is proper. Finish. Now go to isometric view again, fit all, and we can see the fields. This is the exciting port 1, this is port 2. Okay. Now Now in this case, this is just a waveguide. So in this case, what we can set the offset as 0 mm, so it will not extend anything beyond. So let us try this one, but I'm making it as a variable d. So in d I am giving 0 mm. Okay. So now you can see the region, and we should fill it with air. Now, no. So now we create this analysis setup, and in this analysis setup, I am going to go to select and select a broadband frequency spectrum, and I have taken this length L as 15 mm. So for 15 mm, I might be getting 2A lambda x. So it will be around 10 gigahertz. So I'm starting with sorry, for air-filled waveguide we might be having it at 10 gigahertz, but as we have filled this material with an FR4, so it will downgrade around 6 gigahertz. So I'm starting simulation from 4 gigahertz to 12 gigahertz, and maximum number of samples I am selecting as 10. Maximum number of passes I am selecting as 10, and I am clicking it OK. Okay. Then for we'll be using fast sweep and select the field, right click. Now we start validation. It is OK. So let us simulate and see what are the results. This one is an SIW project. Okay, again there was some problem. So if we see the selection, this progress, that solution data. In solution data, we can see that for a setup 1, we have completed 2 passes, and our error is this one. Okay, so at this point, we have just got in 2 steps we got the simulation, this convergence. Now let us explore what are the results. So right click here, go to rectangular plot, and we will be plotting S11 and S21. So now, as we were expecting, the frequency is very low. So, sorry. Here, what you can see, go to X marker. Now, here you can see that S11 and S21 both are very near. So that means the field is not in being going inside the waveguide, and at this point we can see that this transmission coefficient, it is representing that our signal is traveling between port 1 and port 2. So the cutoff frequency of this waveguide is about 5 gigahertz, and you can see this S21, it has the maximum value of S21 is minus 3 dB. That means only 50% of the power is being transmitted to second port. So if we try to see that, go to top and let us make this invisible. Now create a sheet And whenever we have some simulation results present, at that time if we are creating an object, so ANSYS asks us if you want to create a non-model object. So what does that mean? That means that non-model object will not affect your results, so your results will be saved. So I want to keep my results, so let us click yes, and then I want to create a sheet like this, and I will position this sheet in z axis, let us call it ZP, so that we can vary this sheet and see their positions. Right now I am keeping it at h by 2, and let us go here, go to isometric view. So you can see this sheet is intersecting with our results. Now select this sheet, right click, go to plot field, E field, magnitude of E, and here from the sweep we can select the frequency. Let us start with 4 gigahertz and click OK. So now let us go to the field view, select this one. So at 4 gigahertz, what we can see, our waveguide, this sheet has an electric field like this. So if we start it from uh, minus 10 to plus 10, and in y we are starting from 0, x is 20 mm, uh, and y we are selecting up to L. So now this sheet you can see, I think minus 10. Oh. So I made a mistake here. If we click on the fit all, you will see that the sheet that I just created, it has shifted here. So the reason was, here I have not put the dimensions. So here I put this 10 mm and here 20 mm. Click OK. Now fit all. So now the sheet is present at this point. So now what you can see, that the input field is trying to excite insert a field, but that field is not propagating throughout this waveguide. Okay. Now select this frequency to 5 gigahertz. Now you can see at 5 gigahertz this field is propagating, and we can see half, one and half. So it is making two sinusoidal variations here. Let us increase it to 8 gigahertz. In 8 gigahertz, we can see there are multiple half wave variations, and each of these, what you can observe, at this point, the maximum field is too high. It is around 6,300 volt per meter at this point, and at this point we have reduced the to 3,150 around. So approximate half of the electric field is somehow lost. So where this field is lost? This field is lost inside the waveguide itself, because we are having an FR4 material. That FR4 material, it is a very lossy material. Its loss tangent is 0.02 or zero point 0.2, and so we don't whenever we have any device that we are fabricating, if the electromagnetic field is confined inside the waveguide, then we should not be using FR4. Okay. So in waveguide, or in the dielectric field waveguide, our field will be confined by the waveguide. So we will not be using this FR4, because from this simulation what we have observed, at least half of the power is being lost. Okay. Now if I decrease the length to 50 mm and try to simulate it again, Now let us go to results and check the solution data. See how fast did we convert. Okay. In this case also we are converging in two steps. Uh, in two steps we are converging. And the simulation is very fast here. Now you can see for max. If you select here, now the S11 is -2, -1.9, -1.8, like so. At this point, we are getting a maximum transfer from port 1 to port 2. So basically, waveguide is a simple transmission line, but in the transmission line also we are having too much losses. So another solution for this is we change the substrate. Right click here, go to edit. Oh, sorry. Double click on this material. Now go to materials and edit the material. Now we will be using rosers and RT Duroid we will be using. You can select the material based on the availability in your labs and click apply. Now again click simulate this, because as we have changed the material, all the results have been discarded. Now simulate it again. So now we will be having a shift in the cutoff frequency of this waveguide. The waveguide work as a high pass filter, so it is ignoring the small frequencies. Earlier we had around 4.5 gigahertz or 5 gigahertz was the frequency. Now I am expecting around 7.5 gigahertz of frequency. Okay, so let us see. Now we can see this 6.5 gigahertz. This is the cutoff frequency of this waveguide. And if you go here, the S21 is nearly zero. It is -1.17 here. So it is below -0.2 dB. That means our 99% of the power is being transmitted from port 1 to port 2. Okay, again this was for your design in a waveguide. This is a normal waveguide. Now what we need to do, we need to move this waveguide. So instead of creating the sites, these sites, let me copy this one and click paste. Now what we will be doing, first we select these sites and move the site to inside the substrate. So let us say WA, and WA I am selecting as 12 mm. Okay, so now what we can see, this side 1, this is inside this substrate, this side 2 is also inside this substrate. Now when I click on the validator, then I will be getting some error, and I have previously told you the reason. If you can think of, this is giving an error, 3D model error. So what it is saying, the part of side 1 and top intersecting, side 1 and substrate intersecting, side 1 as ground is intersecting. So what is happening, this side 1 is extending from 0 to h plus 2t. What we can do, we can select here and start it from t, and its height should be h. Now this object will be submerged inside the substrate only. So at this point we are not getting any error. Okay, now click here, clear all the messages, and now again start simulation. Okay, so as we have moved this side walls inside the substrate, so the width of that waveguide is reduced. So as the width reduces, our cutoff frequency will increase. So now let us say now the cutoff frequency is 8.1 gigahertz. Now and we are watching the field as 10 8 gigahertz. So let us move it to 9 gigahertz and double click here so we can see the field. Now you can see the field is like this, and if I uh, drop it at 12 gigahertz, the field is like this. So now from the S21 we can find out the how much losses are there. So here we are getting very negligible losses inside the dielectric because the wave is starting from port 1. If you click here, this is your port 1. The wave is being fed from this port and it is being received at this port, and the wave is confined inside this dielectric. So in the Rogers material also we are getting a loss of 0.2 dB minimum. Okay. Now what we can do with this is a can we implement this one? Can we fabricate this kind of structure on a PCB? If anyone has ever tried, can you explain? Can we fabricate this kind of structure? Can or more specifically, can we implement this side wall inside the substrate? There is no solution for this. Okay, so that is why what we are trying to do, we are trying to first we analyze the uh, effect of thick dielectric field waveguide with very thin height. So in that case also we are can see that the waveguide properties are there. It is giving isolation, and due to the dielectric losses there are some losses. Otherwise the waveguide is working perfectly fine. So dielectric field waveguide with very thin height will work perfectly, but we are left with the problem that how we can implement these side walls. This is the only problem we are facing. So in to resolve this problem, let us create a copy of this one, and I will save it. Now what we can do, instead of this continuous side wall, what happens if I create a copy some small walls? For example, I have deleted that. Only one side wall is there. Now what I will be doing, the length of this side wall I am giving it LA, LX, see, and LX is 1 mm. I am setting it to 1 mm. So now my wall is only this much. Now what I can do, I can create a copy of this along here, and this time I will make sure that I select this attach to origin object, and I will select this total numbers to a variable. Right now I am clicking 2 and OK. Now it has created an object that is directly attached here. Now click here, and I will give this movement as LM, and I'm selecting is 1.5 mm, and the total numbers I am making it variable, and I will not give it a unit, any unit, and let us say I want 10-15 objects, and click apply. So now you can make the number of objects variable only when you are attaching it to original variable. If you are not attaching, then you cannot make it variable here. Okay, so now we see, and let me guess if we can set this to what should be the maximum value. We have a 1 mm thickness, so we can have 1.5 gap, around 30 uh, 35. 35 is much more. Let us make it 34. Okay. So this kind of slits we can have this kind of slits, 34 slits. And now let me create a copy of this one, a mirror image. And okay. So these two, we add them, unite them. Now let us see what happens. Now there is O2 wave must have soul inside object. Okay. So I think our design has extended beyond port 2. So we can change this number to 33. Now let us try. Okay, now it is working. So now if we see at this point what we are seeing, this area, it is going, the S parameter are positive here. So this is not possible at any cost. So why this is happening? Because our simulation ran into some errors. So let's go and check what happened here. Go to the results, check the solution data. In solution data, go to convergence. We have this result, but we are at somehow at this point we are getting the positive values. The reason might be with associated with the meshing and the convergence. So if we select here, go to mesh, so okay, let us avoid this one for now. We will be resolving this later. So beyond this point, what you can observe that at beyond this point we are having this S21 less uh, minus 0.27, and here the return loss is increased. Okay, so this should not have been there. And now if we see the field here, this field is we can see this field is confined inside these holes. Now what happens if we decrease the number of holes? These are small slits. So if we want to decrease the slits here, let us say I want only 20 slits, and still I want them to be distributed along the whole length. So what I can do, I can increase this one. I can increase this one to 2.2 or make it 3. 3 is very much. 2.8, 2.5. Okay. So now what I have done, I have changed the spacing between these slits. Now let us go and simulate. Now when I am simulating this, so here what you can observe, if we go to solution data, check the convergence. It took around 4 passes. Earlier it got resolved in 3 passes, and now we go here, select this one. So now you can see that this has increased, and it is also returning at the same port. From here you can see some field is slightly going backside. Now let me reduce the number of slits again. Let's say I want only 10 slits. So the width will be, okay, 10 will be 15 slits and 3 mm, 3.2, 3.5. Let us try with this one. Okay. Now the spacing between the two slits is 3.5 mm, and we are trying to run this. Okay, so at this point, what we can see from results, go to solution data and see the convergence here. It has taken 9 passes. Now with this one in 10th pass also it did not converge. And see the number of elements that were solved during this. In the first iteration, in the first pass, the number of elements were 1100. Now it has from 1100 to 3500. That means almost 3 times the elements are there. Still it did not converge. So that is why we are achieving getting these spikes. If our solution gets converged properly, then we will not be getting these spikes. And again we are able to see that the S21 is right here. But if we see the solution here, go to the top view. Now at this point, if I click here and go to animate this field, so what you can observe here, at this point between these slits, the field is trying to get outside, right? The field is trying to move past these slits in between these gaps. Now if I decrease this number of slits to 10, and this will become 5, and click here 5.2. Okay, now if I simulate this, then we will be able to see that the field is leaking from these side walls, because we don't have a continuous side wall, we have only slits here. Okay, now another question that comes in our mind, that is why the researchers are using these cylindrical holes instead of this slit. As we were just simulating, and we observed that in these slits we are getting good results, right? But why the researchers are using cylindrical holes instead of slits? So what happens in simulation, we can simulate anything. If we can implement these slits, we can also implement the complete continuous walls also. So then there will be no problem at all, but we were not able to make that hole. Then we are not able to make these rectangular slits also. Whatever we are doing, we are going to drill that, and when we are drilling, then that drill bit will have a circular shape, right? So we can only drill the holes, and we are not increasing this length. Okay, so these slots are smaller, so that will also decrease. Now if you see here on top, now right click and animate this field, so here you will be able to see the proper leakage. So from these points the field is being leaking, and we have no other medium here, that is why it is not being shown, but the field is leaking here. Now uh, here we were considering that we can produce these kind of slits that have zero thickness, and they are perfect here. But if we replace these slits with rectangle, sorry, with cylinders, what will happen? So now I will make a duplicate copy of this one, and now I will be replacing this with cylinders. Now we want to replace the slits with cylinders. So let us say this is the cylinder, and I will put it at WA, sorry, WA by 2, and length I'm considering that we will be taking a cylinder of radius R. So R is not available. RA I am going to select. What is the minimum drill bit size you can think of? If you have ever used the bits, if you have ever used the device uh, fabrication prototyping machines, then you will observe that the minimum dimension, minimum diameter that we can select, that is 0.6 mm. So the minimum radius that we will be using, that will be 0.3 mm. This is the minimum we can go in most of the uh, prototyping machines that cost around 25 to 30 lakh. This is the limitation for the drilling bits. Okay, now select the radius RA, and height we are going to select H. It will start from T in Z direction, and along the y-axis where we should be putting it around 2 times the radius of A. Okay, so now go to top and select the cylinder, select fit. Now I will zoom out a little bit. Okay, so now what you can see, this cylinder is placed nearby this edge, and if I had selected this to R, then you see that this is just touching this edge. So at this point we will be getting some non-manifold errors. So that is why I am selecting this R as I am starting this from 2 into RA. So that is this point. This is your RA, and this is the point that I have put. So now this is 2 RA, and then we assign it a material. We are assigning it copper material because we will drill and then we will be filling that with copper. Okay, so now this is just one wire, and then what happens, that side wall that was continuous, first we replaced that with slits, then these slits are also not feasible, so we are replacing them with cylindrical wires. Now that diameter of these wires is D, So in our case, it is 0.6 mm, and the wall that we want to implement, it has a dimension of A. Okay, so the effective length of this waveguide, effective width of this waveguide can be calculated from this formula. So where did we put this cylinder? We put this cylinder at WA by 2. So WA is 12 mm. You can put it 12 minus 0.6 square divided by 0.95 times S. This S is the spacing between two consecutive wires. So when we select this cylinder, click on the duplicate along the line and move like this. So make sure you are attaching this original object. Then what you can do, you can go here and select this spacing as 0.6. So what we would be preferring, we should have the spacing between 1 mm around. Then numbers, we are again making it a variable. Okay, so now from the top view, let me make this select this one and fit selected, and let us try to play with this parameter S. If I make it 0.6, both the two cylinders, they will touch each other, and at those touching points we will be getting an error. Okay, and but the question comes, if we can implement like this, we will be able to implement the regular wires, right? We can implement the continuous wall if I put it like 0.3. So you can see this edge will act as a wall, continuous wall. But what happens if we have too many holes in our PCB? That will also degrade your quality of and strength of the PCB. So we cannot have that. And at 0.6 it is touching each other, that will give some error. So we increase it to 1 mm, and there is a formula between for this, that the spacing should follow a particular formula so that it does not leak. I don't have it right. So these are the parameters that D should be less than 0.2 times of lambda g, and the spacing should be less than 2 times of diameter of that. So in our case, we have radius 0.3, diameter is 0.6. So maximum value of S we can select 2. Okay. So now we have selected the maximum value. Now we need to calculate the numbers along this line. So what we can do, in the N, we can put L minus 2 times RA divided by S. So it is coming around 41. So we can have 41 wires along this line. Okay. So we have created 41 wires. Then again we make a mirror of this wall and select this 0 0 0 and 1 comma 0 0. Okay, so now we have successfully created this wire, and this wall we have created. Now let us try to simulate it again. So at this point, let us go to results and continuously check what is the convergence. Okay. So this time we might get some error. Let us also open the taskbar and open this memory watcher. We will be continuously monitoring our RAM, because as we have increased the number of elements, these wires, they are increasing our mesh size. So because of that, we will be occupying more space there. I think it has converged somehow. Okay, so it has converged. Now also I think we might be having some positive values of the S parameters. Okay, so no positive value of the S parameter, but you can see that the variation in S22 is like this. Okay, and if we see the field, go to field, you can see this field is. So now the thing is, we have implemented this via this wall at the same position width of WA. Now go to here and see what is the frequency here. It is 8.5 gigahertz, whereas in our previous case we had this around here 7.5. Okay, if we go to the previous results, we had this around here. Go to this one. At this point we are having a frequency 8.2 gigahertz, and at the same points we are implementing this wall. This is our normal waveguide, and normal waveguide with a width of 12 mm. In that case we are having a cutoff frequency, not this one. In this case we are having a cutoff frequency of 8.1 gigahertz, and we have when we have implemented the same wall with these cylinders, at that point we are getting a cutoff frequency of 8.56 gigahertz. So the cutoff frequency is increased. That means in our SIW, the frequency, the effective width is decreased. So that is mentioned in that formula. The effective width of the SIW will be given by this formula, and the cutoff frequency will be given by this formula. That is the standard formula, C by 2A, 2 width. So here we have taken this, the effect of epsilon r also. So in this way you can create your waveguides SIW. So this is how you implement an SIW. Now we will design an SIW slot antenna. For that, let us select this one, copy this and paste. In SIW slot antennas, I will okay. So in what happens in SIW slot antenna, we design the SIW and we short circuit this end. So here also we are placing conductive wires, and that will act as a wall, and the one of the end of the waveguide is closed. Then from the end of this waveguide at a distance of lambda g by 2, here lambda g is the guide wavelength. Okay, at this distance we will be placing our slots. We can either plate these slots in horizontal or vertical. Okay, in horizontal position we will be having a separate polarization, in vertical position we will be having a separate polarization. So uh, in case we want to close one of the end, then what we need to do, we need to copy this cylinder and remove these duplicates. The cylinder is still here. I will move it to L minus 2RA. Okay. Now I will make a copy of this cylinder along x-axis. and again attach this to original one. Then I will vary this one to the spacing of S and N2. So N2 I will select as let us try make it 8. Click OK. So 8 is less. We can increase this one. Let us make it 12 mm. 12 mm 1.2. So we 11. Okay. So in 11 wires we are able to match this width. Okay. And now let us try to simulate this one. So we had two ports here. One excitation was given at this port and another excitation is given at this port. So when we have added this conductive wall here, then there is no meaning of exciting from here. So we remove this one and we also remove that face. Again, we select this object and give it a face. Now, the error that we were having earlier was because this waveport that we have selected that was extending beyond the walls. So that might have been giving some error. So let us remove this one and I will create a copy. I will create a sheet instead of taking from face. So this sheet, I have created a sheet, make it orthogonal to y direction. It is starting, it should start from the width, waveguide. So it was minus WA by 2, 0, 0. And then in X it is varying up to WA. And in Z it is varying up to H plus 2 times T. So it is starting from 0 and it is touching lower and upper both of the copper plates. Okay. Now you can see this is the waveguide and now I select this one and go to front. Select this. If it's selected, right click on this and go to excitation, ports, wave port, create a integration line again and click next and finish. Now fit all, go to isometric view and start simulation. Okay, so now you can see that S21 is disabled because we have only one port. Now check what is the value of S11. It is appearing like this. So this is our cutoff frequency and S11 is 0. That means all the power is being reflected back. So some of the power is going inside beyond this point inside the waveguide and then returning back. Okay, but in this case it was not even going inside the waveguide. That is why it is like this. Okay, so now what we need to do, we need to consider this region only from 8 gigahertz to 12 gigahertz. So let us change this and go to setup and select the wave frequency to 10 gigahertz. Click OK. Select the sweep from 8 gigahertz to 12 gigahertz. Now what we can do, we can create a slot. Okay, so this time again it is also whether we want to create a non-model object. So this time whatever object we are creating, we want that object to have effect on our results. So let us click on No. Now let us create an object like this and give it. It will start from L minus 2 times RA, that is this edge. From this edge, we will be having a displacement of lambda g by 4. So LG4. Let us give it LG4 and LG by, it should be LG by 4. So I am giving it name 0 L minus 2 times RA minus LG underscore 4. So I can remember this one. And we want to cut the slot on the top of the waveguide. So on top of the waveguide, we can create this. We can we will be having height h plus t. It should start from h plus t, and LG4 I am giving it randomly some value 8 mm. Now in the x-axis, we don't want it to start from 0. We want to have some offset, x offset. Okay, I will explain the meaning of this x offset. So right now give it 0.5 mm, and x thickness I am selecting as 2 mm. The slot length I am selecting as 12 mm. The Z size is T, that is sufficient. Okay. So okay. Now this is the point, the starting point. So L should be in negative direction. So now we have this float here. Okay, and if we go here, we see that the center point of the slot was lambda g by 4. Okay, so the center point in that case LG, we, let us call it L slot, and it is 12 mm, and the width we are giving width W slot, this is 2 mm. Okay, and L slot is minus L slot, and Z is T. And let us go here, make it positive. Okay, so now what we can set this. So the spacing between this edge and this point is lambda g by 4. So lambda g by 4 is L slot by 2 plus some space. So we have this lambda g by 4. So we set it this lambda g by 4 to 2 mm. Now it is okay. Now before we start, we subtract this slot from here. What we can do, we can have some rotation in this slot, and let us give it a rotation. Okay, sorry, rotation we will consider later. So now we have this slot placed along this side, this, and this is the main axis. This y-axis is the main axis of the waveguide, and this slot is slightly offset in the right side, because if we put the slot in the center, then there will be no radiations. If we make this on the slide, then we will be having some variations. So now let us, from top side, let us cut this slot. So now you can see on the substrate we have a slot. Now click here, close, and analyze all. So now if we see, due to the energy imbalance, we are getting this spike here. So we need to optimize it better. We should be changing the setup here. From here, we will be setting it to higher levels and increase number of passes. Then we will not get this error. And still, in the S parameters, what we can observe, this is a peak here. This is a dip here. So we might be getting resonance here. So how do we make sure that we are getting a resonance here? Change this report to real part of the impedance, real and imaginary parts. So now at this point we are seeing that there are multiple resonance points. So what is happening here? If you see this resonance point, it is 8.5 gigahertz, then 9 gigahertz, 9.75 gigahertz. So at 8 gigahertz, this has just started. Then we have 9 gigahertz. It is giving half wave variations, half sine 1.5 times. This is a quarter wave variation, and this is half wave. Then we are having 10.7 gigahertz maybe. So for the frequencies at which we are having this one half wave, two half wave, three half wave, and a quarter half wave or full half wave, at those points we will be getting this resonance. Otherwise, if we are getting a resonance, that is due to our antenna. So at 11 gigahertz, there is, so let's make sure we have 11 gigahertz. So at 11 gigahertz, we can see we have this waveguide, and this is your quarter wave. So 1, 2, 3, three half waves and one quarter wave. So at these points, we will be getting some simulation results. And now let us see these results. This is S11, this is the waveguide. And so how do we calculate this length of the slope? Okay, how to get electric field intensity with respect to patch length. So with respect to patch length, what do you mean by that? This is your if you want to measure see the length, you can create a sheet, and on that sheet you can display your results. Okay, and now if you right click here, right click and modify plot, not like this. When you click on this field distribution, you can select this field calculator. In this field calculator, you can insert this, select these fields to be evaluated, and from here you will be able to select what kind of operation you want to perform. Okay, then at some point you will be asked, maybe behind here, in which volume you want to calculate the field, and you can set this calculation. So that at some point you want to calculate the exact point of exact value of the electric field, or you want to simulate de determine the uh, dev deviation, or you want to find out the maximum or minimum field, you can calculate, select these functions, and you can add them in evaluation. Okay, and then we have created this. Now let us try to make this slot smaller. So if you don't have an exact dimension, then also these simulation tools make our life easier. So we can just play with the dimensions, and even someone who has no idea about antenna or electromagnetics, they can also learn this and try to simulate, and they can say, I have created an antenna. These are the results that were expected. Anyways, so if you are not sure how to calculate the length, then you can always go to ChatGPT or any AI tools. Like go to ChatGPT, ask it to calculate length of the slot wave of waveguide slot antenna operating at 10 gigahertz. The cutoff frequency of the waveguide is 8 gigahertz. Okay, so we give this these tools this, and because the formula is a little bit complicated to calculate exact dimensions, so we come up with this. So here it is calculating the dimensions of the waveguide, open the guide wavelength it is calculating, then it is calculating L length of the slot is 25 mm. So we should be using 25 mm, and the guide wavelength was 50. 25. Okay. Let us go to that calculation. I think there is something wrong with their calculation, but still let us give it a 20 mm and see what happens. Okay, I recalled what is the error here. Still, we will not getting any results here. Okay, the results are same, just those positive values of S parameter are removed. So the problem might be because if we go to then this view and we select this region. So this region is just touching over surface, all six sides it is touching. So because D is 0, now let us set this D to 50 mm, and in negative y we set it this padding to 0. Now if we, okay, D 50 mm is too much, I will make it 20 mm. Now let us try to simulate again. Okay, if you are working in SIW antenna, you should read this book. This book has a very detailed explanation about the concepts from very basic, and it has many examples. And there is a PDF version available online. You can search for that. And now the error was due to this one. So now I will make this length again. So how did I concur that this one is the right result? Because you can see from this slot some part is radiated. Therefore it is not showing anything here. So I will just go here and reset my length to 10 mm. Now let us simulate again, and hopefully this time we will be getting a cutoff frequency around 11 gigahertz. So this result was 24 because it might have not considered the waveguide field. Uh, the waveguide is filled with dielectric material RT duroid. Okay, so as the material is filled with RT duroid, it is calculating this lambda naught to 30, and in dielectric it is 20 mm. The guide wavelength that is around 34 mm, and from that it is calculating just half, but it is not a direct relationship between the guide wavelength and the slot wavelength. So now it is saying 16 mm. Okay, so we might be getting around 10 gigahertz or 12 gigahertz. We might be getting a result here. Okay, so now you can see we have many spikes here, and the extra resonant points that we got, those are due to the slot. And now if we see the slot distribution, and what we can do to fasten this simulation, we can reduce the size. So now from 50 we reduce it by to 30 mm, and we reduce the n to be from 50, 20, 41. Let us make it 20, 23, 24. Okay, so now let us try this again. So the thing is, we need to calculate the uh, wavelength from this. What we can see, our slot should be placed. The center of our slot should be lambda g by 4 distance from the short circuit. Then we should be having a distance of lambda g by 2 if we have multiple slots. Otherwise, we should close at this point only. Okay. So first, what we need to do, we need to see the from the field distribution. We will be taking a different approach now. Let us wait for the field distribution, then I will check into that. Now you can see up to this point we have not reached the convergence. At this point only we got the convergence results. So the thing is, we should be having either 3 lambda g by 4 length of the SIW, or 5 lambda g by 4, or 7 lambda g by 4. This SIW should have, this SIW should have this 3 lambda g by 4, or 5 lambda g by 4, or 7 lambda g by 4 length. Then only we will be having a good antenna design here. So at this point we are floating at 11 gigahertz. It is not at 10 gigahertz. The length is slightly increased. So, and at 11 gigahertz it is like this. So we can also calculate the guide wavelength. If you go to model solutions, click here and select this lambda. Then if you plot this, this is giving you the guide, uh, the results. So this is your guide wavelength in meters. This is your guide wavelength. So if we calculate at 10 gigahertz, the guide wavelength is 34 mm inside this simulation. So the guide wavelength is 34 mm. So if we make it 3 lambda by 34 into 3 by 4, that will give us around 26 or 27 mm in length. So this length, we make it 27 mm. Then we decrease the number of points, number of copies, and 20, 21, 22. Okay, so let us make it 21, and instead of, we make it 1.21 spacing, or 1.22. We have slightly increased the spacing between two consecutive wires. Now this exact dimension of that one guide wavelength is 34. So 34 by 2 or 4, we should be having our slot placed at 34 by 2. So at 34 by 2 or 4, we should be having 8, 9 mm of distance. So X slot, I am keeping this X to be 10. So 5 plus 4. This one is 4. So now let us simulate this one. Again, one more thing. We should make the slots smaller. Then on this slot, I'm giving one more variable. I'm giving this top. Okay, G. Now I'm giving it G equal to 1 mm. So when I'm G is 1 mm, then originally that object was not even intersecting with our top. So this top has no cut here. Okay. So first what we will doing, we will be verifying that our length is lambda G by 3 lambda G by 4. From the field view, we will monitor that. So now if we see the field view here, it is at 11 gigahertz and it is showing two complete half cycles. At 8 gigahertz, 18 gigahertz is not there. In 8 gigahertz, the field is like this. We go for 10 gigahertz. At 10 gigahertz, we are having half and quarter, 3 by 4 variations we are having. Now, we should be placing our cut around this point. The center should be around here, and when I put select this one, make it G0. So I think we have placed it correctly. Let us analyze it again. And we will be checking one more parameter, that is port impedance. Okay. Once the result complete, I will explain what it is. So this is the wave port impedance of the wave that we are facing at the wave port. So you can see at this point, the impedance value is around 67 ohm. Okay, and beyond that it is decreasing. And S parameters, again this error is because of the uh, uh, because of the simulation convergence criteria and the radiation box criteria. So in radiation box, what is happening? Okay, so here what has happened in radiation box in this region, we have not assigned any boundary. So if you assign this boundary here, go to this and click radiation boundary and select OK. Now at this point, now we will be not getting those spikes. So basically in the whole session, we are just copying one design into another. So only one time we have set these boundaries. That is why I forgot this one. Okay, and still there. Okay, so I will explore it more why this is happening, and we have not got any results. Okay, so now you can see around 10 gigahertz we are getting something, but the impedance is too high. This at this we are getting a resonance, but the impedance is too high. So how do we reduce this impedance? To reduce this impedance, what we can do, go here and first let us see what we can do. We can add a parametric and go to parametric, add a variation for x offset. This x offset, that is very useful for controlling the impedance. And let me make some variation, I'm varying it three variations. Then we will analyze what is happening. So again, if we see here, so this load is slightly lower at the lower side of this point. So we can also move this load upside Okay, slightly, so that the center of the slot and this center point of this point is are the same, and in that way we will be able to get a good result. First, let us see what is happening with this real part of the impedance and change the values. So now you can see that as x of is 0.1, 0.5, the impedance is at this point, and now it is 1200. So we need to match this impedance, and I think today we will not be able to cover that one. So I will continue with tomorrow with this simulation, and then also we will add some transition points like this one, because here we are placing a wave port. So when we are connecting this in our PCB, then we will be feeding this antenna with the with the microstrip lines. So for that we will be needing some transition. So tomorrow I will explain this transition design also, and we will optimize this SIW projects. So now I have to leave. So Swati, can we continue with tomorrow's session?
Yes,
And
sir, we can continue tomorrow
okay.
also.
So one of the question is how to get electric field intensity with respect to patch. I think I have covered this. And if you want to use this multiple modes, then you have to design your wave port and uh, give the excitation accordingly. So I will try to cover that tomorrow also. Okay. Okay.
Participants can ask the question.
You want to know the title of this and paper? Okay. So I think I can give that.
Yes, it cover, but
Yeah. And this is the paper, and I will also share the PDF with Swati, so she will share with you. Okay.
Okay, sir, I'll share it.
Any more? Okay, actually, my Swati,
Yes, sir.
if there are no questions, I would like to leave because the office is closing.
Okay,
Okay,
sir. Oh,
so I will continue it tomorrow.
sure. Thank you
Okay,
very much,
thank
sir.
you. Thank you.
Thank you. Dear participants, next from tomorrow we will have the day 5. You are requested to kindly join by 8:45 in order to avoid any delay in starting of the session. Thank you, everyone.